Up to now, we've been building models for many particles, many identical particles. And in the last lecture, we came up with a very compact representation for a system of an indeterminate number of bosons or fermions. We could always write such a system in terms of these quantum fields, psi dagger and psi of x. So we argued that we could always write a Hamiltonian, at least in non-relativistic quantum mechanics, in this form here. And these quantum field operators, psi x and psi dagger of x, obey the canonical anti-commutation or commutation relations, depending on whether these are bosons or fermions. Now that's fantastic. We've finally succeeded in our task of specifying the kinematics and dynamics of a system of many particles, an indeterminate number of particles. But that brings us no closer to doing actual physics unless we can actually solve such systems. So generally speaking, I'm aware of three, I suppose, four ways of solving systems like this. I know of, roughly speaking, four ways to solve a system like this. So the first one is reserved for geniuses. That's finding exact solutions. It happens every now and again that someone works out an exact solution, and that is, generally speaking, a big deal, because then we can use that exact solution to learn a lot about a new interacting system. But it's not a very good general purpose method, because you pretty much have to have some kind of insight into some incredibly deep maths or physics in order to find these things. So I don't recommend finding exact solutions as a way to solving dynamics. The second approach, this is much better. This is a general purpose method, and that's called the variational method. I started describing that last lecture and will continue today. This is getting better and better. The more variational classes we build, the better the variational classes we build, the more we can apply this method. And the nice thing about the variational method is that every single exact solution helps us build better variational classes. So the quality of variational methods can only improve as time passes and we learn more about the physics of these systems. There's a complete other approach to solving these models, and that's using perturbation theory. This is a completely general purpose method. You start somewhere, you add a small parameter, usually V here. This potential is small, and then you perturb developed Taylor series in the smallness of V. This is an excellent method and has been finely tuned over the past decades to give spectacularly accurate results. We will just super briefly talk about perturbation theory in this course, but you've already met it in your first year. Quantum mechanics is no different. The formula are exactly the same. And finally, I just said there's everything else. There are other approaches to solving systems like this. I just mentioned one, the beta ansatz, which is a completely morally backwards way of solving these systems. You start with a solution and then you find the Hamiltonian that it's the solution for, morally speaking, I suppose. And so there are other methods, semi-classics. I'm not sure if you can call the semi-classical method truly a method of solution, but it's a general purpose method of solution. But it's certainly an approach to getting results out of these systems. And there are a bunch of other sort of approaches. But if you were given a Hamiltonian like this to study and as a model of some experiment, then the first two things you should try, the absolute first two things are, well, three. I mean, first you check, is there an exact solution? Failing that, the first two things you try are the variational method and perturbation theory. And like 9 times out of 10, 99 times out of 100, one or both of those methods will give you almost all the insight you need to understand the system. And that's why I'm going to tell you a little bit about both of these methods as applied to some of the most important examples of this Hamiltonian that we have in practice. To talk about the variational method, we need a variational class. It's no good just to say you vary over some states. We need to have some states to vary over. And the thing we want from our states is that we can compute quantities, expectation values of these states easily. And in the last lecture, I introduced such a class called the coherent states. And we're going to use that class today to understand the physics of models that look like this Hamiltonian at the top. I'll just recall the definition of coherent states that we wrote out in the previous lecture. If we have a collection of operators A, mu, which obey bosonic commutation relations, then so what's a coherent state? It's an eigenstate of the annihilation operator A mu, and a many-mode coherent state is just an eigenstate of all the annihilation operators for your system. And there's one coherent state for every complex number, alpha mu. Any list of complex numbers, alpha mu. And we're going to use exactly these states as a variational class. There's really multiple reasons why this is a good variational class. So let me give you some reasons why certain classes of states are better than others. So a class of states is a good variational class if it's the exact solution of some natural class of models. If you can write down some simple models that you can exactly solve that are somehow physical, then that's a good class of states to use, the exact solutions of these models, because you know it's going to be right, at least for those models. So that's a good start. And the coherent states are exactly states like this. Coherent states are the solutions of quadratic models, or subset of. So let me say this. Coherent states are ground states of certain natural class of Hamiltonian. That's the first thing to note. So models of bosons and fermions, actually everything I say is true for fermions, but we won't do the fermion case in this course. Coherent states are the ground states of models that have this form here, which are most quadratic in the annihilation and creation operators. So this is already kind of an amazing result, right? Because it turns out lots of models have this form in practice. This models, quadratic models, and turn out as like first order approximations to the physics of all kinds of systems. And if you like, these are non-interacting systems, because if you express this Hamiltonian here in terms of annihilation and creation operators, which you can do, of course, remember I showed you in the last lecture how to do that, then this term here gives you the quadratic stuff that corresponds, roughly speaking, to that. But, of course, you've got quartic stuff here. This is the interacting part. This is what makes life difficult. This term here, well, this cannot be usually expressed in quadratic terms unless you make some kind of approximation. Nonetheless, this turns out to be, these terms here turn out to be easy to approximate by quadratic terms in lots of interesting situations. And so we end up with lots of effective models like this. So coherent states are a good place to start studying the physics of many-body systems, because they're already the solution of a class of many-body systems. And that's why we're going to use them as a variational class. And I'm going to do, today I'm going to do two calculations, or roughly speaking, it's the same calculation, but sort of twice, with these coherent states. And we're going to show how to solve, well, I guess this model in relative generality using the variational method, as we'll see. But as a warm-up, I'm not going to solve this field model first. We'll write down a simpler model just to get used to the variational method and this variational class. I'm going to write down now a model, a non-trivial model. Let's add all right. This thing here, this is a model of bosons. It's called the This is a model of bosons called the Bose-Hubbard model. What's it useful for? Well, imagine you have a ring and you have a periodic potential on this ring. And you have bosons moving in this ring. So we got, I'll draw the bosons as little blobs. So we've got n potential minima around the ring. We have bosons moving in this potential, and then we make lots of approximations. So this is the situation. We're getting to this, we're getting to the period in time where we can engineer this model effectively in experiments with dilute ultra-cold atomic gases. And so it's becoming increasingly important effective model. So the way, how do you get this boson effect, the Bose-Hubbard model? Well, you first put on a strong periodic potential V naught in a ring. Usually people put it in a line. We can imagine that we have it in a ring. You condense or you cool down as many bosonic particles as you can in this ring, and you reduce the temperature lower and lower and lower until the bosons want to sit in the potential minima here. They're repelled from the potential maxima. The bosons rather sit in the potential minima. Now the bosons do feel each other's presence. If there's another boson at the same location, that gives an energy cost, which is this term here. It's a repulsion term. This term here is a chemical potential term. It models the fact that you've got some atoms, you've got an excess of atoms outside the trap and they want to move into this lattice geometry here. And there's some probability amplitude for the bosons to tunnel to neighboring sites. So that's very, very brief summary of the physics that gets you of this part here. So if you make lots of approximations to this model here, the full interacting Hamiltonian of n bosons, or an indeterminate number of bosons, then you end up with this model here. So this is what's left of the kinetic energy. That term there. So each of these terms has its antecedent or origin in these terms here, in the original model. What we're going to do today is just take this as a model by itself and try and solve it. These operators obey their bosons, so they obey the canonical commutation relations, J, K, I. And since we've eliminated or ignored or integrated out all the other degrees of freedom, there's in fact only n of these operators here, and we have periodic boundary conditions. Otherwise known as PBCs, where j equals 0 is equivalent to j equals n. So I hope that's enough data to specify this model. It's not a trivial model to solve. When capital J is not equal to 0, we can't solve this model exactly, or at least I don't know of exact solutions. If you want to earn eternal fame and glory, I guess you could try and exactly solve that model. Especially in 2 dimensions. Here I've just put it on a ring, but the models that are actually being realized in laboratories right now are 2-dimensional versions of this model. They certainly have not been solved. Although, if you were to exactly solve it, I doubt we would learn much new, because it turns out that the variational method and perturbation theory have taught us an extraordinarily large amount about the physics of this model. So the effort in somehow finding an exact solution may not even be worth it. So let's actually study this model using the variational method. There's multiple variational classes we could choose here. We could choose Fock states, we could choose coherent states, which is what we will do, and so on and so on. There are, I think I can say safely that there are thousands of papers on the solution of this model. Not hundreds, but thousands. Not tens of thousands, but definitely order of magnitude 10 to the 3. So if we're going to do the variational method, we need a class of states to vary over. This is the variational class, and they're none other than the coherent states that we defined in the previous board. There they are. That's a big old class of states. It's infinite dimensional, in the sense that this is an infinite list of complex numbers here. Except, of course, we don't have an infinite set of modes today. We've only got up to n minus 1. N modes. Oops. we've actually got only n modes because we've integrated out and ignored and eliminated all the other modes that were relevant for solving that model up there. This is the variational class here we're going to use. And how do you do the variational method? Well, you just take the inf, the infimum, over all the states in your variational class of the expectation over the energy. Like so. And it's at this moment that we see why these coherent states is such a good class of states to study. Because we can calculate this expectation value analytically in terms of the alphas. That's what makes this class such an amazing class to work with. So let's actually do that. Let's calculate this object here, this function. So f of alpha what is that? Let's start calculating. Well, actually, what we're going to do is we're going to make our lives a lot simpler. Our life is going to be made simpler in that we know that this model has a symmetry, yeah? It's got this rotation symmetry. If I translate j to j plus 1, then I get the same Hamiltonian. So we're actually going to, we realize that the variational minima will probably respect that symmetry. I say the word probably, but it doesn't necessarily have to. If you design the variational class badly, it doesn't necessarily represent the symmetry. Sometimes the class will break the symmetry that a Hamiltonian has. There's no guarantees about symmetry in the variational method. But we could just exploit the fact that we know that under j maps to j plus 1, h maps to h, right? So if you translate, if you rotate the ring by one side, you get exactly the same Hamiltonian. So, you know, it's a reasonable thing to do to guess that the variational states that we should use should respect that symmetry. And that'll reduce our problem from an n-dimensional search problem to a one-dimensional search problem, as we'll see. So instead of doing our variation over the full V, we're actually going to do a variation over a much smaller variational class, namely VTI, which is just comprised of all coherent states alpha bar of the form alpha, alpha, alpha on the 0th, 1, 2nd, or the one n minus 1th mode. So I'll just write the word symmetry here. Yo.
I don't understand why the Hamiltonian stays the same if we do this transform.
So the question is, why does the Hamiltonian stay the same if we do this transformation here? J goes to j plus 1. So what I'll do is I'll write it out here. I'm going to modify in place this definition here, and we'll hopefully see that we get the same Hamiltonian at the end. All right, we're going to do that transformation now. J goes to j plus 1. So let's look here. Okay, wherever I see a j, I've got to put a j plus 1. So that's j plus 2, plus 1, plus 1, plus 2. Here is plus 1. And here we've got a plus 1, plus 1. That's the transformation. I've just done it. Now we're going to check, can we get back our original Hamiltonian from this one here? So we're going to set up a dummy variable, j prime. J prime goes from 1 j prime is j plus 1, so it goes from 1 to n, but remember we're identifying n with 0. So then that's, what is this? Well, this is just j prime plus 1, j prime, j prime, j prime plus 1, and so on. So we get back the same Hamiltonian. So that's why that I get used to doing this calculation so much I forget that it needs a proof. So yeah, I hope that that at least justifies why that's a symmetry. And then once you have a symmetry, it's very natural. Like you would think if the Hamiltonian has a symmetry and it has a unique ground state, then we know that that ground state has to have that symmetry. So it's very tempting to guess that your variational class should have that symmetry as well. However, be warned, the variational method does not necessarily want to preserve symmetries. In fact, if it can get a lower energy by breaking symmetries, it will. It does not care about your symmetries. It just cares about getting a lower energy. That's why you have to be very careful about imposing symmetries in the variational method. Adding constraints does not improve an optimization problem. So this is an optimization problem where taking the infimum of something over something. If I add constraints and restrict this class, this infimum cannot be lower, it can only be larger. So be careful. But in this case, I claim that this is a good start to getting an understanding of the physics of this model. All right, so we're going to use this as a variational class now. Namely the translation invariant coherent states. And now we're going to try and work out the energy. And the first thing we note is that the first term is going to vanish. If I remember correctly. No, maybe it doesn't. No, it doesn't vanish, right? No, of course it does not vanish. It stays. What I will do is leave this board there for a moment. And we'll go through term by term the contributions to f of alpha. Let's look at the first term. The first term is this, the remnant of the kinetic energy. And let's work out what is the expectation value of this kinetic energy term with respect to one of our variational class states. So here it is. That's the first term in that Hamiltonian there, which comprises, if you count it in one way, 1, 2, 3, 4, 5 terms. Let's just do this term. Okay, we'll look at that term there. We're going to work out the expectation value of that thing. Well, it turns out that's really super easy because when you apply A to a coherent state, you get alpha. That's the whole point. And if you take the dagger of that, if you apply a dagger to the bra alpha, you get alpha bar. Simple. So actually, we get the following answer when we calculate that term. That was great, right? So this thing that I've called the kinetic energy now evaluates to 2 times n times minus t alpha squared. N sites. T is just t, which is some number, and then done. Well, let's look at the next term. This is probably the most complicated term in the whole thing. Okay, well, a little bit of it's pretty easy. We can do that bit easy enough and that bit easy enough. No problems, right? Oh, there's J's still. All right, but this is not in a form that we can evaluate straight away. See the problem? Coherent states like A's when they're applied to them, but they don't like A daggers. A daggers are not their thing at all. But there's something we can do. We can reorder this term by using the canonical commutation relations. So we know that A times A dagger minus A dagger times A is the identity. So this is just the identity plus A dagger A. And then we get our final answer, which is that 1 plus alpha squared. That's that term. And then all the rest are easy. So I claim that we've now got the answer. So f of alpha, what is it? Well, it's minus 2n t alpha squared. That's that first term, plus j, plus n times j, because you get the same thing n times, this thing here. All right. And then you've got another term in the j symbol here, but that's minus j n alpha squared. Yep. And we've got another one. Final term, mu n alpha squared, like that. So that's our function. And we're going to minimize this function over all the alphas, all the values of alpha. So the variational method, what does it want you to do? Yep. Because our variational, so the question is, why do we get alphas without an index? Well, our variational class to begin with had a different alpha at each side. But then I argued that the model is translation invariant, so we can focus on a subset. I didn't write it out. We're instead going to do the variational method. Yeah, sorry, I didn't write that out. So we're going to do the variational method according to this subset here. Of course, you could leave the alphas in, and actually, in this case, I do believe you find that all the alphas have to be the same, although I haven't done that for a while, so I can't remember exactly. So we're trying to take the infimum of a function f, and that function f is a function of a complex number alpha. Now this is ordinary, we're now to ordinary calculus. So we're taking the infimum over all complex numbers alpha of the function f of alpha. Now just by looking at the expression for alpha, you see that if you do things in polar coordinates, then nothing depends on theta. So this is equivalent to taking the infimum over r in the positive real numbers of the following expression. Minus 2nt r squared plus nj r squared minus r to the 4 minus j n r squared plus r squared. But you see that r squared appears everywhere, so you may as well make a change of variable. RSTQ, I guess I'll use, we're on x. I'm going to try and do a simplification now on the fly. This might go wrong. Is that correct? This cancels, yeah? Pretty sure that cancels. JN. Yeah. Oops. X. And we got one term here, njx squared. So we finally reduced this problem to something we can actually solve, which is the minimization of a quadratic. Thank heavens. So that's pretty good. Now let's work out the answer. Now usually in practice, when you do the variational method, you don't end up with a quadratic. We got lucky today. We got lucky because I chose the example so we'd get a quadratic. But in general, you could get some horrendous function of x here, something really terrible. But at least it's a function of x, of some number. And that, although you can't write out the analytic solution often as not, you can stick it in a computer and run Newton's method on it, and that'll find you a local minima. And you might be worried that, well, Newton's method is not guaranteed to converge, blah, blah, blah. Which is all true, but in practice, you just run it a couple of times, and if you get the same answer over and over again, you become convinced. And then, if you go to your friendly experimentalists and ask them, do they get the same answer? And they say yes, then you're convinced, right? And that's actually, indeed, in practice, how many people study these models. They reduce it to a numerical search problem, which you can do with a computer. Computers are very fast today. In fact, in my lifetime, my research lifetime, from when I got my PhD to now, I've seen 4 or 5 orders of magnitude improvement in the results for studying models like this, of which, let's say, 2 of those orders of magnitude have been due to Moore's law, due to computers just getting faster. But actually, computers stopped getting faster a little while ago. They're still running at 3 gigahertz. Most CPUs still run at 3 gigahertz. So actually many of the improvements have come in developing better methods to minimize these nasty polynomials. It's an interesting question what's going to happen now that Moore's law has really bottomed out, it's really flattened out. We're not really seeing any improvements in computer speed anymore. If you've been following the release of Intel's new CPUs, you'll see that they're only giving like 10% improvements in these kind of calculations. So doublings are gone. We're really under pressure now to either develop better parallel methods to take advantage of problems like this, because it's easy to make copies of things, or indeed to come up with more and more efficient methods. So for the past 10 years, we've had a free lunch when it comes to variational calculations, but now we're back in a tough time again. We want to take the infimum of this quadratic polynomial here. Well, we know how to do this, right? So there's an x there, and we've got minus, and in fact there's a common factor of n throughout the whole calculation, so we can put that out the front. And we've got minus j x squared, x, minus 2t plus mu. Unless I've made a mistake. I think that's right. All right. I forgot a minus, huh? Yeah, I did, thank you. Okay, so, well, we got to find where the zeros of this polynomial are, and, well, we could differentiate this polynomial to find where the derivative is 0. How about we do that instead? So we get, I'm going to just drop the n from now on because the location of the, got to leave the minus sign in there, otherwise that turns into a supremum. So we got that. We're going to take the derivative of this thing here. So the derivative of that is minus jx plus 2t minus mu, and plus minus jx. Is that right? Yeah. Okay, the infimum is at that, the solution to this linear equation. All right, linear equations, we're good. We can do this. So this is minus 2jx equals mu minus 2t minus plus. There it is. Although actually, I think we could have worked this out simpler. So this is a negative x squared. So we know it's a parabola that points like this. And it's 0 here. No, we want the supremum, right? The infimum of, oh no. All Okay. In the case that j is greater than 0. Yep.
I think the right-hand side on the last two lines should have another minus. So it should be plus mu and minus 2t.
All right. You think there's another minus sign on here? So there's plus. Really? Oh yeah. Good. Actually, the solution to this is pretty boring if j is positive. This function looks like this. As long as mu is bigger than 2t. And in fact, the infimum occurs here or here. The more interesting case is definitely when j is less than 0. And then this whole thing gets flipped. Why is this? I wonder if I've just written down the model the wrong way, which is why.
I think the mistake is a bit earlier because when you calculated the expectation value of that long term, you had a 1 plus alpha squared. And
Yes.
in the line below, it's 1 minus alpha squared.
Oh, look at that. Thank you. Okay, that's the problem. So I was very puzzled why I got this picture here, because this is when physics can help you out. And the infimum of this function here is easy to calculate, right? It's minus infinity. So this is kind of bad. So I knew there was something wrong, but I couldn't tell where. Okay, so the proposal is that I made a mistake here. I think that's right, isn't it? I made a mistake right there. Yeah. Let's see if I can propagate that through and make this correct finally. Nj alpha to the 4. It's a plus there. It's a plus there. So this is a minus here. Oh, well, that's even what? Okay. This must be a plus then, huh? Yes. And now the parabola is the right way. Okay. That's the most important thing. Ah, okay. The world is in order again. We know the minimum is somewhere here, wherever here is. And you can work out here according to this one. I'm just going to finish propagating the mistake through. Plus, so it becomes minus 2t plus u. Everyone's nodding, good. So as long as mu is bigger than 2t, that minimum occurs on the right-hand side, which is over here somewhere. That means if you have a big chemical potential that forces many particles into the system. That's what this interpretation tells us. And now we'll undo all these substitutions. The solution is any alpha of the form 2t minus mu over 2j squared e to the I phi. Pretty sure that's it. Remember, x is square root of r, or r squared, sorry. It's square root. There we go. That's the answer to our variational calculation right there. Other way around, of course. Yeah. Good. That's how you variationally solve the Bose-Hubbard model. And actually, in this calculation, we encountered all the kinds of complications that you encounter in any variational calculation. And for the rest of this lecture, I'm going to generalize what we just learned. This was a warm-up exercise just to get us ready to tackle the full Hamiltonian. And because this was also, because we managed to, in this calculation, see all the difficulties we're going to see in general, it's going to be really easy to do this final calculation. Right. Okay, so let's do this. We're going to solve a quantum field variational problem now. So far I introduced these things called coherent states for a collection of bosonic modes. Now I'm going to define something that you could call the coherent state for a quantum field. It's exactly the same thing, but just masked in a different notation. Now remember what I told you about quantum fields in the previous lecture? They are mathematical phantasms. They're not operators at all. But if you work with them obeying certain rules, then you need never convert to creation and annihilation operators. But you need to have some practice in knowing what's a legal manipulation and what isn't. Today I'm going to show you legal manipulations. Last lecture I showed you illegal manipulations that led you to proving that 0 equals 1. If ever you do a calculation with quantum fields and it doesn't feel right, convert everything to creation and annihilation operators, do the calculation there, and back convert to the quantum fields. That's the only way to be sure. But it's a good, once you get some experience with these things, the quantum fields are just so much easier that you get used to when they work and when they don't. Usually, whenever you find yourself saying the words, I have an eigenstate of position, then you know you're in trouble. Otherwise, you're good. So I'm going to define an operator which you could call the field displacement operator. There it is there, the field displacement operator. Where this phi is playing the role of alpha in our previous calculations. Phi is some sufficiently smooth function from R3 to the complex numbers. So phi is basically this list of complex numbers here, alpha. Indeed, you can make that absolutely rigorously true by defining phi naught, alpha naught, alpha 1, and so on as the Fourier coefficient of phi on the 0th basis vector, 1st basis vector, and so on. So this basically is essentially is, but I'll leave it like that. Well, once you've defined the displacement operator, you can define coherent state. So what's a field coherent state then? It's just what happens when you apply this guy to the vacuum. That was one of the 3 different ways we had of defining coherent states in the last lecture. There you go. That's what a field coherent state is. And it obeys some very nice properties that you would hope it obeys. These are all exercises. But if you know how to do it for the creation and annihilation operators, then I claim you've already done the calculations. So they're not hard exercises. The first thing you might hope, and it is indeed true, is that if you apply a field annihilation operator to a field coherent state, you'd better hope that that's somehow an eigenstate, right? That's kind of the best analogy you could hope for. Indeed, that is the case. I'll write out the exact assertion now. If you take the field annihilation operator at position x, remember this is not an operator, right? Then indeed it is true that a field coherent state is an eigenvector of that operator, even though it's not an operator. This expression only makes sense when you integrate it against a smooth function. Remember, field operators are boxes that eat smooth functions for breakfast. That's property number 1. How could you prove this property? Well, the only way to be sure is, as I said, to go back to the basis, the creation and annihilation operators. But a way you could convince yourself that it's true is to use the algebra of these field operators. So this is, as I said, an exercise, but I'll give you a hint on how to do this exercise. Hint. To do this exercise, you could look at the commutator between psi x and the displacement operator as written up there. So look at that thing. That's sort of hint number 1. The second part of the hint is you know that psi hat of x is on omega is 0. Basically completely per definition. Now, how do we do this commutator though? Well, that's a bit of a pain, right? There's an integral and blah, blah, blah. So I can't quite help you out here, except to say, just discretize that integral, replace it with a Riemann sum, and then that should help you. I don't know, there's another way of doing it, come to think of it. Yeah, I'll show you this way of doing it. So, how do we get this commutator here? Well, look at the following thing. Let's call it psi hat s comma x. Here's a neat little trick you can use to calculate objects like this. So D turns out to be unitary, which is something you can check. And we're going to set up an equation of motion for psi hat conjugated by this unitary D. So if D is a unitary, then D to the S is a unitary. And we're going to solve a differential equation in S in order to work out what d dagger psi d is. So a very neat trick to calculating all kinds of quantities in physics is you don't calculate the object itself, you rather differentiate it and then use the fundamental theorem of calculus to get the answer. And you can do this derivative here. You can actually differentiate the exponent of this object here, and you get an equation of motion. And the answer is something like this is all an exercise. And at this point you're basically done because you integrate now. And that, I think, is enough data to fully complete the exercise. Right, so that's one way of convincing yourself of this fact. There's multiple other ways. So convince yourself however you like that psi hat applied to phi is phi of phi. There's another fact that's true. Once you've seen this fact, the next one is easy. The derivative of psi hat is, well, the derivative. We got partials here. Okay, there's another fact about field coherent states that's very useful. And now let's do a full variational calculation with a full Hamiltonian specified in terms of quantum fields. Let's take our variational class now to be all field coherent states defined, all these guys here, defined by functions phi from R3 to C, which is at least twice differentiable. We need 2 times differentiability, as you'll see, in order to define the energy. And now we're going to do a variational calculation, just as before. With respect not to some Bose-Hubbard model, but the full second quantized interacting Hamiltonian. The real deal. Every single term will be present. There's a kinetic energy term, there's a local potential, there's a non-local potential between the particles. That's as nasty as it can get. That's just about every model in non-relativistic physics. Well, we know some stuff about field coherent states that makes our life incredibly easy, right? We know that psi applied to phi is something easy. We know that psi dagger applied to phi bra is something easy. In fact, we know all these things. So we can, in one line, turn this big variation over a gigantic Fock space of an infinite number of infinite dimensional Hilbert space with an indeterminate number of particles into a much, much simpler variational problem, namely this one. Inf over phi of some functional of phi. So here we had a nasty thing that's not even an operator, and then poof, we have a complex function. That is pretty amazing. Because what we've done is we've reduced a problem of finding the minimum eigenvalue of some horrendously complicated infinite dimensional operator to something just involving ordinary functions. So this is a thing called a functional, right? And we've encountered things like this before. This looks like an action. This should make you think of an action in terms of the action principle and Lagrangians. And we know how to find infimums of things like this. Yep.
Question.
Yep.
T and V0 operators?
T and V0 operators, that's a good question.
We have to take the expectation.
Yes, they are operators. They're still operators, but on this function class here. I'll write out what they are. So from the last lecture, T stands for minus h bar squared grad squared over 2m. So it's an operator on functions. V naught is usually just some multiplication operator, such as, I don't know, some local potential V naught on x, phi x, like that. So they're both operators, but on the single particle space. And when you encounter an object like this, what is this? It's a box. Let's call this box E, and this box eats a function phi. It eats derivatives of phi, and it eats second derivatives of phi. And the reason it eats first and second derivatives is because of this grad in here, right? We've got grad squared of phi, so it's got to be eating those objects. And you can either use integration by parts to get it to be in terms of two of these or just one of these. So it's an object that's eating those things, and we're going to try the infimum of it. But there's a trick to doing that you learned many years ago now. We can always extremize such functionals like this via something called the Euler-Lagrange equations. The Euler-Lagrange equations give the extrema condition for this functional. And that allows us to write out an equation, a constraint equation on the phi's. Not any phi will do. If phi is the infimum of this expression, then it must obey an equation. And I'll write out that equation. And then we'll stop for today. So Euler-Lagrange equations give some differential equation for phi. Remember how Euler-Lagrange equations work? So it's d e d phi minus d e, well, that's the Euler-Lagrange equations right there. And of course, they're complex conjugates. And this gives us an equation of motion that constrains phi, the minimizer of this expression here. So it's pretty complicated when V is general, so I'm going to do it for a very super simple example, which is nevertheless of extremely relevant practical importance. So suppose the potential between these particles is a delta function. They don't have any, there's no cost for the particles to be apart, but to be on the same location, there's a delta cost. You have to be a bit worried if this makes sense, but it does, I claim. In this simple example here, then this L of phi, the condition that phi has to satisfy in order to minimize the energy according to the variational method, has a very special form. Namely this. So the field coherent state that achieves the minimum energy, the minimum variational energy with respect to this very complicated interacting Hamiltonian, has to satisfy an equation, and this equation is a very special form. It looks like a Schrödinger equation, a stationary Schrödinger equation. The first part is stationary Schrödinger. Plus there's a nonlinear term here. This is a third order in phi. And this equation has a name. It's called the time-independent Gross-Pitaevskii equation. And it's the, you can interpret it in this context as telling you what is the optimal coherent state that models this interacting atomic system. Now the story isn't finished yet. You still have to solve this equation in order to find the variational minimum, but this is something you can discretize and put in MATLAB. It's not very complicated. Okay, so we'll stop there for today. And next week we'll move on to electron gases. Thank you.